This is a integrity video for Handout 31 in Math 146. Later in this video I'll go over some of the things at the beginning, but I wanted to start with the question at the end, which is right here. Now the first thing about this question, like any question, is that it has some sort of a question or claim that we're asking. And in this case, it's whether or not the average of something is less than 2.5. So that claim or question has to be represented by our alternative, and of course the null is just the same thing with an equal sign. Now we're really ready to calculate the test statistic in this question. So here's the test statistic formula right here. Z equals the sample mean minus the mean of the sample mean divided by the population standard deviation over the square root of the sample size. Now many of these numbers should be pretty straightforward. It says the standard deviation is assumed from other studies to be 0.75. Well, just like in chapter 7, when we say that, we're talking about the population standard deviation sigma, so this is 0.75. It says there's a sample of 80, that's our sample size n, so that number has to be 80. And then it says that the sample mean, the average time of the sample, is 2.37, so that number goes here. And finally, this last number, 2.5, well, that's really coming from the null hypothesis. So notice that you learned in section 6.4 that the population mean and the mean of the sample means must be the same number. And when we test the null hypothesis, we're assuming that this is true. So that means that the mean, the population mean, and also the mean of the sample means, which is going to equal the same number, are both going to equal 2.5. And so we're testing the null hypothesis. That number goes here, and our data number goes here. That's our sample mean from collecting this sample of 80. So when you think about a test statistic, think about the numerator as being kind of a measure of whether or not the data and the null hypothesis agree or are in conflict. So the farther apart these two numbers are, the more they're in conflict, and the closer together, the more they agree. And of course, the more they agree, the less likely you'll reject the null. And the less they agree, the more likely that you'll reject the null. Now, the next thing to consider is our p-value, or calculate our p-value. And in this problem, since we're doing a left-tailed test, our p-value is the area to the left of the test statistic. So that comes out 0.06057. And then we have to compare that to our alpha, and anytime our p-value is larger than our alpha, we're going to fail to reject the null and fail to accept the alternative. We'll talk more about this later, but the p-value is kind of like a measure of how unusual this sample mean is. So this sample mean of 2.37 for a sample of 80, if we assume the null is true, is not that unusual. We'd get something that unusual or more about 6% of the time. So that's not strong enough for us to decide to reject our null. So we fail to reject our null. Now, we still have to write a conclusion. Last part of the problem, and kind of the trickiest, especially at first, is to write a conclusion that addresses the original question or claim. Now, to do that, where's our original question or claim? Well, I've highlighted it in red here. The question is this average less than 2.5? And that went into our alternative, not our null. So I'm not really going to be talking about rejecting the null here. I'm going to be talking about accepting the alternative in my final conclusion, since my question or claim is in my alternative, is not in my null. So my final conclusion will not talk about rejecting something. It'll talk about accepting or proving something, or supporting it. Now what is it accepting or proving? Well, the claim. And we can say data not sufficient because we failed to reject the null. That's really all there is to it. Now, just here's a question. We failed to reject the null. What could have made the result different? You might think about that for a second. And there's a couple things that would have made the result different. One is this sample mean could have been smaller. So it was 2.37, but a smaller number might have made this a smaller negative number and would have made that p-value smaller, would have meant that this was more unusual. There was more of a conflict between these two numbers here. Another thing that could have actually helped was to make the sample size larger, because the larger your data, the more robust your results, and this number being larger would also make this a smaller negative number. In fact, I can tell you that if the sample mean had been anything from 2.3 or below, or if the sample size, say the sample mean has still been 2.37, but the sample size had been at least 181, well, then this test statistic would have been small enough that the p-value would have been less than 1%. Or in other words, this would have been something like negative 2.3 something. And that would have been small enough so that the p-value would have been less than 1%. So we can check what we just did on our calculator as follows. Notice that I've hit the stat key and moved over here to the tests menu. And right away I'm on number 1, the z-test, so if I press enter, I will get something that looks like this. Now right now it says to input data, but I want to change that to stat. Okay, now stats is highlighted right here, and I've put in my sigma is 0.75, my sample mean is 2.37, my sample size is 80. I have a left tail test, so I've circled the less than here, or I've highlighted the less than among these three choices here. If it was the right tail test, it would be the greater than. Two tail test, the not equal to. And this mu naught is the mean from the null hypothesis, so that's the 2.5. So then I'll go calculate and see what comes up. And there's our results. There's the same p-value and the same test statistic that we saw already. So this calculator function will check all that for you.